is all too often an elephant in the room. It's only referred to by engineering anoraks, who know a lot about how it works, but little about why it's needed. It's very much about the dynamics of sound in the real world. The most common sound that we encounter is the sound of the human voice. And this is most often heard, of course, when face to face with another person. It's conversation with spoken words and gestures and facial expressions and body language. The understanding of it is a subtle mixture of all those things. If the human speech is a recording, then much of that subtlety is missing. A recording can compensate for the missing information to a large extent by making sure that the words are clearly and distinctly heard, by increasing the volume of the quiet bits and controlling loudness by compression. The basics of a compressor are that it should clarify sound by increasing its perceived volume. Practically, that cannot be achieved just by turning up the volume. To avoid a chaos of loud sounds, it's also necessary to control the volume of those parts of the sound that are already loud. This all sounds obvious, but it's actually quite tricky. The volume of sound needs to be increased for low volumes and decreased for high volumes, and to make the process sound natural, the timing of these changes is really critical. A test tone is suddenly switched from a volume level of minus 10 dB up to 0 dB. That's multiplying it by 3. On the computer plot, you can see the spike as the compressor grabs the control of the audio. The volume stabilizes to a volume level of about minus 9 dB within a few milliseconds. Then, when the test tone is switched back down to minus 10 dB, the volume, in this case, smoothly reverts back to the minus 10 dB level in about half a second. This plot uses a feedback analog compressor where the electronics sense the volume of level at the output and use it to modify the volume setting of the input. Digital compressors can work in a different way, where the input volume is sensed and can instruct the input stage to modify its gain to suit exactly. Technically, it's a more perfect solution to the problem. However, unfortunately, that's not how the real world works. Human hearing reacts much more like the analog optical compressor in the computer plot. A sudden increase of volume can trigger a reduction in hearing sensitivity. And similarly, when things are quiet, ear sensitivity increases. These effects are slight and generally not noticeable, except in extreme instances like in a rock concert, where ear sensitivity can vary hugely as volume rises and falls. In the recording studio, compressors have a hugely important role. They're rarely used nowadays as leveling amplifiers, as they were originally called, but mostly as artistic tools to tighten up the sound or to hold together a mix. But let's move on to limiters. Correctly, a compressor is designed to reduce dynamic range. It will increase the general volume level and decrease the loud passages. A limiter is designed to prevent the output of an audio amplifier from exceeding a predetermined level. It should not affect the sound in any other way. In the real world, the definitions of compression and limiting, they become confused. Compressors are often used to control output levels, while limiters are often used as compressors. The most effective limiters are normally digital. The ability of the circuitry to see ahead and adjust to suit any overloads that are coming has to be the best possible design. However, there's a continuing flaw in this argument. The limiter sees an incoming overload. It then signals the next amplifier stage, and instructs it to reduce its gain. So in a complex musical signal, it's a momentary reduction of the volume of the complete signal. It's true that it's a short-term effect, but there has to be a sensible release time to the limiting, and this has to be audible. It's true that there have been many devices designed to improve the effects of limiters, often by splitting the audio into bands and treating them separately. But the criticism remains. The perfect limiter is one where the original audio signal remains at a constant volume level, but where momentary overloads are prevented from breaking through. These seem to be mutually exclusive. You can't remove spikes and overloads without adversely affecting the main body of the audio signal. True, but the world of audio dynamic control is full of psychoacoustic effects that control our perception of sound. It's possible to take advantage of the sensitivity of our hearing to get around this problem. By careful use of a diode clipper, one can control or even eliminate momentary spikes of sound. Getting very slightly mathematical, the perceived volume level of this audio signal is the integral of the waveform, or to be clearer, it can be said to be the area under the curve. If the audio signal is momentarily reduced by a conventional limiter, the perceived volume dips. If the signal is clipped, there is no apparent dip. The way this soft clipper works is like this. While the overload or spike is present, it's removed by a partial short circuit through a series of diodes. This momentarily distorts the waveform, but it's a very short duration, and the distortion shows as a series of harmonics that appear and disappear too fast to be appreciable. As far as the listener is concerned, as long as the overload was not too extreme, the overload did not exist, and there was no difference to the original signal. Designing a new Pi compressor product is a continuing challenge because the original Pi 4061, as used by the BBC, used the principle of variable pulse width modulation, a difficult process that in my experience was never completely successful. In my design, I've taken a new look at the problem so that I can reproduce a product with similar controls, but using a more reliable and predictable compression medium, the optical cell. But the details of that I must leave for another video. In the meantime, it's back to the computer.